Hi Toby. Sorry I didn't get back to you sooner. I had friends around this weekend, but I hope this is helpful. So this is actually a really cool question. Um, Now, when you've done volumes of revolution, the way I can imagine and the way that I usually introduce it is um, thinking about lots of discs and then you're adding them up. So here you can imagine that this is like a slice as you spin this around the y-axis and you're adding up lots of these discs to make up the area. Now, when you think about that, how you'd work out your volume then is it'd be the sum of all of these pi x squareds, because that's the circle on the top, and then you get this width, which is your delta y. So you're basically adding up lots and lots of those discs. But in this question, that becomes quite problematic because if we've got this function, I'm then going to have to rearrange this to make x a subject and then square it. So I'll get a squared inverse cosine, which is really, really tough to integrate. So there is an equivalent way of you imagining this area, and it's instead thinking of taking away two cylinders. And it doesn't often get talked about, but it's a really useful technique because the formula you get at the end, you don't have to square something. You end up just timesing it by x. So what I would do instead is we can imagine it as all of this being the radius. So I'd have x plus this delta x all squared. And then I'm going to multiply that. That's my radius. So then I'd have pi to get my circle across the top and multiply it by y. And that would give me the whole of this like cylinder as I go down. And because this is a function, it won't just be a straight line, the y, it will change as that curve changes. So you'll end up getting this matching as you go down the curve basically, and it will keep giving you the equivalent piece of the disc that you want when you take them away. I've forgotten to write in that I'm going to take away the inside bit of the disc. So I'd end up with pi x squared, and then to make sure that it's that cylinder again, I'd do that. And I'd be adding up lots of those. Okay? Now, I've looked at the solution, and I think actually Madas goes through and does the derivation just to save time. What happens then is you end up with 2 pi x y dx. Okay, so that's the equivalent formula. They'll give you the same thing. But the advantage of using this in this question is I don't have to rearrange it to make x a subject, because I'm just going to times it by x. And I don't have to worry about rearranging this y. So that's actually quite a cool thing for me to do this. So when we go about substituting this in, we end up with the integral. I'm going to put the 2 pi on the outside because it's constant and it's not going to affect anything. And then I'm just going to get x times by 1 plus cosine of 2x dx. Okay? Sorry, my Apple Pencil is really not very good at the moment. It's really laggy. So what's going on? There we go. Just done it again. So we get this. Now the next thing that's maybe a stumbling block and making you not being able to do the integration is at this point in the course, you've done some reversing the product rule, and you've done some integrating trig, but you've not done something called integration by parts. Okay? Now, that in itself is how you would do this integral, because when you expand this bracket to make it something that you can integrate, the x is fine, but you get this product term, which is x2 cosine 2x. And I'll just put my limits in that I'm going to integrate between those. Okay. Now, you haven't done this formula, okay? But essentially, when you want to integrate a product, you can do reversing the product rule, but there is another formula as well that you'll meet next year. And a bit like the product rule, we use u and v substitutions. Bear with my Apple Pencil. There we go. And if I want to integrate u dv dx, I'm going to end up using this side of the formula. Okay? That means that I have to label my x term, my u, and the derivative dv dx is actually this cosine bit. So when I work out what v is, I end up integrating this part of the function, and then I end up integrating the other part in this part of the integral. So that's why it gets its name. You're doing the integration in two parts to do it. Okay. I have already done that working, so if I just grab this with my Apple Pencil, because it's being really annoying, and put it underneath. There we go. You can see that in this bit here, if I get my laser pointer, I've chosen the x to be u, and that's useful because when I differentiate it to get my du, it disappears. I just get a constant. Now, in this part of the formula, I've got my v, and that's come from me integrating the cosine 2x. But because the x now, has become a constant when I differentiate it, I don't have a product to integrate when I do this second bit of the formula. So that's why it's useful, is that if you've got x at the front, you can choose that as your u, and then it becomes a constant, and we get this removal of a product in the integration. Okay. Each of these I've just had to do using reversing the chain rule. So I know that cosine integrates to sine, so I've got sine 2x. But if I just wrote down sine 2x, when I differentiate it, I get this extra 2 come out the front from being the inside function, and I need to cancel it out by using a half. Okay. Yeah, so don't worry, you haven't done that yet, and that is sort of halfway through year 13 that we actually end up doing that. The ones that you'll be in your test will be those reversing the product rule ones, which have just got like polynomials or powers of x with brackets and things. Okay. I hope that's helpful. And yeah, looking at some of the rest of those questions, they're pretty hard, those ones. So yeah, good work. Anything else? Let me know, and I'll get back to you. All right, bye.